Now let's take a look at the fundamental design requirements and working principles of the Line 2 isolator. The EU GMP defines an isolator as a decontaminated unit with an internal work zone meeting Grade A conditions that provides uncompromised, continuous isolation of its interior from the external environment, for example, surrounding cleanroom air and personnel. The design of isolators follows four basic principles. Must provide a workspace that is separated from the surrounding environment that meets GMP Grade A cleanliness standard while performing processes. Must provide a way to transfer sterile materials into and out of isolator without introducing microbiological contaminants. Must provide an ergonomic way for work to be performed inside the isolator from the outside without compromising its integrity. And the internal space and exposed surfaces must be microbiologically controlled. The filling line isolator is located at Genentech Hillsborough in the manufacturing building in the Grade C filling room. The primary purpose of the filling line isolator is to protect the product from contamination by enclosing the entire filling and capping machines in an aseptic Grade A ISO 5 environment. The isolator creates a physical barrier to the external Grade C ISO 7 environment and workers. The Line 2 isolator is a rigid wall isolator made from stainless steel for the enclosure with laminated safety glass for viewing windows. The control system of the isolator is via the Programmable Logic Controller or PLC that includes the Human Machine Interface or HMI. The Line 2 isolator has an aseptic working chamber, a circulating air zone to create unidirectional or laminar airflow, and an air management system, or HVAC, in the technical area. The air handling equipment in the technical area includes an air handling unit for intake air, 2 filtered fan units for exhaust air, and 2 air heaters for dehumidifying the chamber. The intake air handler is equipped with an air cooler, air heaters, HEPA filter, circulating fan, and related sensors and gauges to ensure and control the temperature, relative humidity, and positive differential pressure in the isolator chamber. The exhaust unit also has a HEPA filter and a pressure gauge for measuring the differential pressure across the filter. The unidirectional airflow within the working chamber of the isolator is created by flowing fan-filtered air through HEPA filters and CG screen that convert turbulent air to laminar air in a vertical direction down to the process machine, over the product and away from the base plate to the air return ducts. The aseptic working chamber of the isolator is the critical area. As we've already learned, the isolator must provide a GMP Grade A environment for the filling machine. This is accomplished by flowing constant and optimized HEPA-filtered air over the filling machine and product that are completely enclosed within the isolator. To maintain this constant, clean airflow, the HEPA filters are measured on each side of the filter by differential pressure sensors. If the differential pressure of a HEPA filter exceeds a predefined value, this is an indication that the filter is blocked and needs to be replaced. An alarm will be shown on the HMI if the value is too high. The Line 2 isolator uses aseptic transfer systems to maintain the sterility of the product as it moves through the filling process. The sterilized empty vials are loaded into the filling isolator via the sterilization tunnel, and the filled vials are transported to the capper machine via a mouse hole. The vertical airflow remains a constant velocity when the openings are closed. When opened, the air velocity increases due to the differential pressure of the isolator to the surrounding area. However, because of the defined pressure cascade, the airflows at the openings is horizontal in the indicated direction and the integrity of the isolator is maintained. Operators interact with the isolator using glove ports, rapid transfer ports, better known as RTPs, and the material transfer airlock, a transfer chamber connected to the isolator that allows materials to be transferred in or out of the isolator and maintain an aseptic environment. Glove ports create a physical barrier between the operator and the working chamber and allow the operator to perform manual work inside the isolator and maintain the grade A environment. To protect the operator from machinery hazards, the glove ports of the isolator are monitored by two separate safety loops. On the inside of the isolator, there are light barriers, and at the outside of the isolator is a control system to check the positions of the glove extenders. During production mode, the inner loop is active so that the machine stops when the light barrier is interrupted. The rapid transfer ports, RTPs, consist of two main components. The port assembly is mounted in the isolator wall, and the can assembly is mobile and used to transfer the materials. Each has a door, seal, and an interlock function. When the two assemblies are mated, equipment, waste, product, or materials can be rapidly transferred into and out of the isolator without breaking containment. The interlocks protect against the port door opening if the can assembly is not fully docked. The isolator is also equipped with a transfer system to transfer stoppers into the isolator. An ATEC system is used. For training on the stopper process, please refer to the Stopper Processor e-learning course. The final way to safely move materials into the aseptic working chamber is via a material transfer airlock, or MTA, with an integrated decontamination system. The material transfer airlock door is closed and sealed on the grade A side and is opened on the grade C side. The MTA is loaded with materials. The decontamination cycle using vaporized hydrogen peroxide is performed via the HMI. Following cycle completion, the MTA door on the grade A side is opened by operators working via glove ports within the grade A area, and the decontaminated materials are moved directly into the aseptic working chamber. The isolator is equipped with a decontamination system designed to provide decontamination of the isolator and filling machine parts enclosed within the isolator chamber with hydrogen peroxide, H2O2. The first decontamination option is the filling line isolator with the MTA. After start of the common decontamination cycle, a combined leak test will be performed. The transfer door is open, and the filling line isolator starts with the decontamination cycle. The next decontamination option is the filling line isolator without the MTA. After start of the standalone decontamination cycle, a leak test will be performed. The transfer door is closed, and the filling line isolator starts with the decontamination cycle. The MTA can be decontaminated independently of the isolator as a third decontamination option. After successful completed standalone decontamination, the airlock goes into the airlock standby mode, and the transfer door can be opened. During the H2O2 surface decontamination, the desired microbial reduction is achieved by the release of gaseous H2O2 into the isolator chamber and the induction of the lethal dose over time.